4 minutes.
The lens,
I have no. Don't worry, I will fill manually.
okay, thank you.
Don't worry about it. This is fine. Yeah, 2 minutes pass. We need to start. We need to do something. Yeah, do something. And what I'm planning for today is a solution of AC network. I need to put a node. We are talking about stable or stationary mode regime of AC network. Not about transients, only stable. We start from the stable. We can do transients, but transients are derived from stable. So it can also be named infinite time regime. I've decided that solving some network from some fantasy isn't funny, so I assembled a small network. But first I need to show one moment where the dog is digging. You see two lines on the screen, yellow and blue. What's yellow, what blue? I have a source. Let's say it's EMF at some sinus omega time, some resistance, not important, and I have a branch with capacitor and resistance. It's all grounded. Very simple. Here I have 600 ohms resistance. This one. And this nice capacitor. It's variable. I can adjust it. Signals. The yellow line is voltage from here. And the blue line is a voltage from this point. Can switch to make them bigger. At this moment, capacitance, okay, half of microfarad. If, for example, here I plug a voltmeter, it will be 1, and I can also plug a voltmeter here, it will be number 2. I'm increasing capacitance. I'm decreasing capacitance. I'm increasing. I'm decreasing. At this moment, 0.1, 1/10 of the microfarad. Can you write second voltage as a function of the first? I'm trying to speak. See, it's a strange thing. There is not only change in magnitude. You see, it change in angle. If U1 is again some U1 maximal multiplied by sinus of double P divided by as a function of time. What will be second voltage? Can you write it? Can you name it? Any ideas? Yellow line is the first one. Amplitude 36.4. So one mark is 36.4 volts. T capital is this distance between this point and this. Since frequency is 1 kilohertz, it will be 1 millisecond. But what will be equation for the second voltage? You have electrotechnic basics in your portfolio. I can write a kilo voltage rule. Where? For example, here. It will be, if here is some current as time, what it will be? I is a function of time multiplied by resistance plus 1 divided by capacitance from 0 to time. E from time, the time equals to 1 as a function of time. Correctly, since by Ohm's law this is function of time, what it will be? It's clearly you see where it leads. Easy to solve. I took a very simple example. You cannot use a simple Ohm law here. Simple, blindly. Because you see this difference. Why? Because of this. Input is a sine, but integrating sine, we got what? Minus cosine. Integrate of sine alpha. The alpha leads us to minus cosine of alpha. Yeah? Yeah. And we see, you see, this 90 degrees shift. What to do? Where to run? And why voltage increases? Okay. Where we are, what to do? Problem. You see problem? It's not easy to solve such network because you need to solve trigonometric equation. I don't like trigonometric equation. Do you like trigonometric equation? No. What to do, where to run? What to do? Any ideas? Call for help? Try to ask ChatGPT. Idea. He is who can help us. history. Take a look, I have a network here. Resistor, capacitance.
Ignore that.
Okay? Resistance, capacitance, network. Have this network. I'm viewing the yellow line is this voltage and the blue line this voltage. I want a mass solution for secondary voltage as a function of primary. I wrote this, it's a second Kirchhoff. Everything fine, but what is there any way to escape from this integral solution? Any idea? Nothing. And you have the electrotechnics theory in your portfolio. I saw. Here is the solution. First idea came from really famous guy Oliver Heaviside and refined by Charles Pratel Steinmetz. Idea is to get ourselves from the swamp of integral differential equation. I can put a coil in place of capacitor. For your understanding, reaction to capacitance change, you think what happens? I will save it. 1 second, I will save this as a reference. Channel 2, here, I would like to show, white line, it's bit out, is a current of capacitor. 1 second, I'll bring a coil here. I will put a coil instead of capacitor. I have coil. Coil.
Yes.
Here is my box of coils. Box of coils. Here it is. White line from capacitor and blue from the coil. Change of inductance. If I put coil here, I got coil here, I'll need to add a member A, D, E from T by easy to solve. I don't think so. Not a. I will take it's a disaster. It's a game. If I took a derivative from the sign, yellow line powering is a sine. If I took derivative from the sign, what I will get?
Which one, sir?
Cosine.
What did you ask?
Derivatives.
Yeah, cosine.
Alpha by d alpha yields to cosine.
Yeah.
But again, okay, this is cosine. This is voltage proportional to current with this resistance. But it's not easy solvable. Solving real circuit means what At some time I'll be in a swamp of integral differential equations. I don't like it. And Heaviside offered a solution. We need to get out of operations like equals or d something by time. How to do it? Where's the solution? Idea is really brilliant. I have something like, for example, I don't know, some x time s from x sine omega plus some angle. Idea lies here. There is an mass area operating with complex number. Let's imagine what exists 1i or 1 or square root from -1. Pure mass says it's impossible. But in real, I can tell, let's imagine. Let's imagine. This means what each number will have a real part, for example A, and imaginary part, for example B, plus u or equals plus square root from -1 plus 1. Or real axis and imaginary. Here is this axis on a complex plane. If this is angle, let's say phi is FC tangents B against A. If this is angle phi, B or imaginary part of x will be what? X magnitude multiplied by sine of this angle. Yeah? Magnitude sine. Magnitude sine. So Heaviside's idea was what's a Heaviside's idea? Let's assume I have a complex plane and I have, let's say, voltage, real voltage. What's the idea of Heaviside? Let's assume it will be, okay, oops, what? This voltage is a projection of some complex vector rotating. How to say shadow? There is something. Light coming from the window. This is my vector. Times 0. Value 0. Shadow grows, reach its maximum, goes down, and goes to the negative and again to 0. So, shadow of rotating bar can be a magnitude of sine like voltage or current, not important. So starting point is assuming what it should,
Be equal.
no, they are not equal. This one is smaller.
Oh.
It should go through 0, should be something like near, closer to this. Okay, it's in some scale. This should be equal to this. So assuming that all these physical values we observe are shadows or projections to imaginary x of some vectors existing, they exist somewhere. That was not enough. Actually, this has started as an idea. Let's assume it has a good foundation inside a Hilbert transform. A real mass foundation for this. Any observable value can be represented as a vector with the help of Hilbert transform. I think first we can start from this simple idea. Let's assume that somewhere exists complex plane, it rotates and shadows. No, projection is actually, in common sense, it's just a shadow. Of these vectors are these values. This will work, but not enough. Idea is we need a power. We need to keep in mind the power. And one trick is done. See, two digits. Amplitude, 23 volts, this one. And second one, RMS. What's an RMS? To make calculus and all this, let's say, EC network handling, close to well-known DC circuits analyze, one special value was introduced. It's called RMS or effective value. Idea, let's say I have two equal resistors. One is connected to DC source and another to my AC source. Of course, there will be a heat. We can say what energy of both sources is equivalent if P1 equals to P2. Since P1 is S squared divided by L, and P2 can be written as 1 divided by period, assuming what this thing is periodic. Integrating from 0 to period, U squared divided by R. We can get a equivalence.
What's the E in this?
Huh?
E.
Which?
A in this.
It's a value of this. This is source.
Okay. It's equal for both. Right?
Yeah. So this E equivalent will be square root 1 divided by period, repetition period, integrating from 0 to period, U squared time V time. So it's an DC source or DC voltage producing as much energy as this AC source. It's called effective value or RMS, root mean square. For pure AC, if U not is some O maximum sinus omega t. E will be O max divided by square root of 2. For pure sine, ratio between effective and amplitude value is square root of 2. You can check in the graph. Knowing what sinus square alpha is 1 minus cosine double alpha divided by 2. It will open. So, in the system of symbolic technique, one trick is done. This, let's say, voltage, this vector of which voltage is assumed to be a fraction is not O max, but O max divided by 2. Effective value. To make calculus simple, they do a trick. They change a scale of complex plane. In general, this should be O max, this should be this distance, 23 volts. But to make calculus simple, it's how to say background convention. Let's assume what vector is not z size, but a RMS size. And all instruments are calibrated to show RMS with some known precision. It's just a starting convention way to prevent blowing their mind. Should I put these two in case of power? Power will be multiplication of current and voltage in some form, yeah? This square root of 2 to get power the same, to power to be a power. We know power from DC. To AC power being near, we or should always divide by 2 or just keep everything clear, assuming what vectors are not amplitude, but amplitude divided by square root of 2 to be an effective value. One step. Next trick. Next trick, current should be proportional to voltage. Yeah? We need an Ohm law. For my network. Here somewhere is an ACM, one capacitor, resistance with voltmeter second, CF. So O1 equals to F plus 1 divided by C, integrating from 0 to time, E not T. To get this will produce cosine. And you see capacitance. Maybe I'll switch back to my capacitor. I'll switch back to my capacitor. Here, I'm changing capacitance. Capacitance very small, 1,000 of microfarad. I'm increasing capacitance. You see, the higher capacitance, the higher current and higher voltage. Okay? This means what capacitance here acts like some kind of resistance, but we have a phase shift. To deal with it, idea of complex or reactive resistance introduced. Both coil and pure capacitance introduce a phase shift of 90 degrees, forward to backward. Voltage, current, you see? Voltage on capacitor is delayed relatively to current. In case of coil, will be an opposite. So idea is, what for coil, XL, J omega L will be used. It's a complex or reactive resistance of the coil. This multiplication is done to reflect cosine. Idea, if you have some complex x, multiplying it by square root of -1 means turn it forward by 90 degrees. Sine and cosine, remember this circuit? Cosine, sine, 90 degrees. Every school must have it. And in opposite, dividing by square root of -1 means turn backward. So, if we, for resistance, you here, will reflect this 90 degree turn. And for capacitance, imaginary resistance introduced. 1 second, I will write it smoothly. Capacitor 1 divided by J omega A. J omega C, what I'm doing. Coil J omega A. Imaginary resistance.
What's the inductance? It's I omega L.
Yeah. Square root from -1.
Okay, it's I on top.
I don't know, you can write it 1e or 1 or simple, all the same. Imaginary square root from -1. Impossible number. You know what hypercomplexes are also exist? These are complex and hypercomplex exist. What people do invent? How will so in time function, U1 as time is I as current and time multiplied by it, and this is U2 by time plus 1 by from 0 to time, E from time, D time. It's in time, in this complex 1. It's an image of first voltage on a complex plane equals to ER plus E J omega C. I can write S. What it will be? 1 divided R plus 1 divided J omega C and multiplied by R. Here it is. Much easier. Heaviside's idea allows to switch from integral differential equations from this form to much easier, much simpler algebraic form with only one tiny moment. All values, really all values will be complex. Will have imaginary part. But solving an algebraic equation much easier in this integral differential form. Okay. Can I solve a network? Network, network, network. Network, network, network. Network, network. I would like to show how I solve a network. What I got? I got an EMF of 15 volts. What means 15 volts? Where is my voltmeter? Oh. Here, voltmeter showing 15. What's in? It means what if I connect it to some resistance, this one, it will produce as much heat as a DC source of 15 volts. It's an effective or RMS. It's an RMS value. Next, resistor 375. And my network.
15 is a total of RMS 1 and RMS 2? Like it's
we
8
don't
plus 7.
No. 15 volts are before resistance. I will show where this
No,
comes.
like it's 8, 1 RMS
Yeah,
1
it's
is 8
RMS
and the RMS 2 is 7. So it is like summing both of.
Yeah, wait 1 second, I will do schematics. Where this voltage are taken? On the one side, I have a coil. Yellow line is taken here. Here, this is my first signal on a scope. I can switch this off. Hey, come on, yellow line, come back. And blue. Oh no. Ugh. 1 second, I will get them back. No. And blue. And RMS. Here. 8 volts will show voltmeter plugged here. And my second branch, it's a capacitor of 1/2 of microfarad and resistor of 600 ohms. Second voltage, blue one, is from here. Ground. And what about coil? My coil is 100 millihenry, but it's not ideal coil. It's also have a wire resistance, 20.3 ohms. So its internal active resistance is 20.3. Here is my network. 1/2. Yeah, 1/2 of microfarad. Oh, yeah. Can we solve it?
We need to find S1 and S2.
We need all voltage, all currents. Let's take everything. Well, we will not do it by hand. The machine will calculate. What's the first step? Base node. Ground, ground, ground. So it's square with the base node. What about, now we can mark nodes and assign numbers. I think this is good for the first node, and this point is good for the second node, where I can attach a scope. Nice? Nice. Now branch, this will be branch number 1, number 2. I think it's good for this to be branch number 3, and this one number 4. Okay? I'm doing the same thing I done with DC networks. Now what I need to conduct nodal matrix, I need to show how nodes are connected with branches. So I will have node 1, node 2, branch 1, branch 2, branch 3, and branch 4. It will be M or nodal first incidence matrix.
1.
If inflows, we write -1. If outflows, again. Branch, node, if inflows, -1, if outflows, 1. So, first branch inflows in node 1, -1. There's no connection to node 2. Second branch flows from node 1. 1, 0. Third branch from 1 to 2. -1, 1. And number 4 flows from the second. Here is my nodal matrix. Yeah?
We can put that also branch number 5?
Where? Here?
20.3, yes.
Yeah, in theory we can do it, but this node isn't acceptable because it's a resistance of the coil's wire.
Oh.
I can't measure voltage here.
Okay.
That's why I assume it's a 1. In reality, it's one nice standard self-inductor type for 1 to 1C. Tinsley, London, SE25. Inside is, because we have a wire inside, it has some ohmic resistance. Coil, wire, resistance. Okay, what I need to do, maybe I can start to program it, or not. One moment, I will start my SciLab. And we can try to put it all inside computer. SciLab, come here. SciLab, come here. Yeah, I got. Okay, open this. I don't need this. I don't need this. I need a new clear file. It should be named somehow. Clear? Fine. Fine. Come here. Come here. Come here. You. Yeah. I put one operator. Clear, it's push or erase. I want a clear, how to say, tabula rasa state. Now, what I'm writing? My M matrix. Minus 1, 1. Wait, one more 1, 0. And on a second row, 2 zeros, minus 1 and 1. Fine. Now I okay it. Maybe bit more arranged. Oh, yeah. First 0 to shift. Oh, maybe something like this. Actually, save it. I don't need a contour solution, actually, but I can do it just for example. Maybe one day you will find you need a contour solution. If I would like to use a contour currents, I need contours. Number of contours is simple. Number of columns in M matrix. Number of rows subtracted from number of columns. I have 4 columns and 2 rows. That means what I need to identify 2 contours here. Easy. This will be contour A and this will be B. It will be connected to the ground. Now I can do what? Contour matrix. Here will be contour, here will be branch. If in one direction +1, if in opposite -1. So. I need to A, B, 1, 2, 3, 4. Let's see. First branch A contour 1, 0. Second 1 here. Whoop, in opposite -1. Third 1 in second and 4 1 in second. Here's my contour matrix. And contour matrix should be 1, 1, 0, 0, 0, and next will be 0, -1, 1, 1. Here they are. Fine? Fine. I can check all this. This one good thing to know about M and N matrix. Multiply of M by transposed N should produce 0. Okay, I will use a bit of my yesterday works. I will take this part and this part. Okay, I can reuse my work. Here what I'm doing. I will use a size function. The size function, it's a measure. First element means what to measure, second how to measure. 1 means number of rows, 2 means number of columns. So MS, it's from Latvian mezglu skaits, number of nodes, ZS from Latvian zaru skaits, number of branches, and KS from contour skaits, number of contours. Here, what means to transpose a matrix? You need to swap rows with columns. That's what I'm doing with help of my hamster wheel. One hamster will run all nodes, second hamster inside will run all branches, and I will swap in transposed matrix. It will be like rotate, it's like rotate 90 degrees. And the same thing I'm doing with the contour matrix. One hamster runs for contours, second hamster runs for branch, swap position. I will not use this, it will fail. This one. So I'm checking the product of nodes branch with nodes contours. Yes, save and execute, and what I got? Nice zeros. Matrix are okay. These matrix are how to say, in harmony between them. Next step. What will be my next step? What I need? I have connection topology, but where are my elements? I have many of elements. Where are resistance? Let's do it by branch. Here small. What will happen here? Resistance will have complex part, imaginary parts. Resistance will be complex. Okay, for the first branch, it's simple, 375. And what about second branch? I have coil and resistance. Watch for the trick. GV equals to complex. Complex is a function. Machine, please create me a complex number. The first element is a real part, and the second one is an imaginary part. 2 by pi by f, frequency. And where is my frequency? Frequency is 1000 Hertz, or what I wrote, 2 by p by frequency. This one is 2pf. Omega angular frequency is double p divided by period, or double p multiplied by frequency in hertz. Omega is a speed in radians per second, and frequency revolutions per second. But I don't need simple omega, I need an imaginary frequency, your omega. That's why I put this multiplication in a place for a complex number. As a result, I will get complex frequency. And what I'm writing for the second branch, 20.3. I need to do it this way. Plus j omega multiplied by 100 millihenry. 100 a minus 3. It will be a minus 3, meaning 100 multiplied by 10 power minus 3, because millihenry. It's 1/10 of the Henry. Next one. What I got for the next one? 1/2 of the microfarad. 1 divided by 0.5 a minus 6, because it's microfarad, and I think I need to multiply by frequency. Yes. Next one, 600 ohms. Here is my small, nice resistance vector. Now I can do full resistance matrix will be diagonal of this small vector. Fine. What I'm missing? An EMF vector. EMF, here, simple. 15 volts for the first branch, 0 for the second, 0 for the third, and also 0 for number 4. Great. Great, great, great. Actually, I'm finished my work because I don't have current sources here. If there would be a current sources, okay, I will just put a plugs for current sources. For I, it will be which one? What can I use? What can I use? Simple. 0, 0. And for E I can use as a plug E multiplied by 0. Fine. These are just to fill them. I can left this one, it will not. It will produce simple 0. What? Semicolon. Wait 1 second. It's because of this space, and this should start on a new row. I think. And have this here. Yeah. Oh, sorry. Yes, now it works. 0, 0, 0, zeros. Fine. Next. What's the next step? Actually, I have my network in. I have presented my network to my computer. Next step, I need to conduct a nodal admittance matrix. Be careful with the C networks. This network will have resistance matrix pure diagonal if your network contain mutually coupled branches with mutual inductance. Non-diagonal elements will appear in resistance matrix, and you cannot just write like a DC, just invert your diagonal. More correct, here is very simple function called Jordan elimination. It's a technique called Jordan elimination. Idea, it's a derivative from Gauss technique, and idea not to move to triangular matrix, but to unity, one matrix. I will put it here. Jordan elimination is a simple way how to perform a matrix inversion. Because matrix must do not have division operation. You need an inverse matrix. So Jordan no, not the player Jordan, the first ancient Jordan. There are many Jordans in history. This one dealt with mass. Also was a famous figure. This one is a French version of Jordan. So that one will be Jordan of inversion of resistance matrix. Yeah, this is our resistance matrix. We need inversion of it. For what? Blah 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 blah. I don't need this. I don't need this to do this thing. I will copy from myself yesterday. Inversion. Next one. I conduct nodal admittance matrix. We do it in DC network. Nodal admittance was M multiplied by inversion of resistance matrix and multiplied by M transposed. Here, nodal admittance matrix have actually its structure GA, B, minus B, GA. What's GA? Real part of. See, if resistance has a complex part, conductance or admittance will also have a complex part. So, nodal admittance matrix will be complex. And resistance will be complex, and solution will be complex, and we will get complex values. Actually, it's a nodal solution. It's the same thing we saw on DC network. Yeah? I just use Y instead of G to note what it's a complex matrix. One moment. Look what we got. Our nodal voltages, see? In complex form. That's what our voltmeter will show. And currents in complex form. Let's check. 9.7, 8.5. See? 9.7, 8.5. 9.7. Here should be 9.7. Yeah? 1.71. And here 858. Let's check what we got here. in reality.
855.
One tiny moment. Do we have a 15 volts at the input? Of course not. 1 second, I will adjust. It was only 15. Oh, 15 volts at the input. 948.
970.
15. 947, somewhere near. And wait 1 second. .5 should be 858. Here 8.5 and channel 1 947 971. Somewhere near. Yeah, 15. Actually looks quite close. .46, 8. Wait, one tiny moment. Can I ask measure? Hey, come on! I want measure. Not phase, not amplitude. Frequency. Close. 1 kilohertz. Fine. Frequency fine. Okay, it is what it is. Do I have time? Yeah, I have time. First I will put a contour solution inside. Contour solution. I need a contour solution. I like contour solutions. Contour solution. This can be left. Here is my contour solution. Again, yesterday I just took it from DC example. Only difference, contour resistance should be, in previous it was NR and transformed. Now it's NZ because imaginary part arrived. All these simple from the DC network. You see, it goes absolutely the same way. I need a result. Oh, look at this. Very nice. It's a difference between nodal voltage and contour solution. I can live with this. Next part. I can add Kirchhoff equation. This part, you saw it in DC. It's my Kirchhoff's equation. The only difference, I put complex here And this is all. Let's check Tirhov. Yeah, fine. BTV. Look, nodal. Here is the structure of nodal admittance matrix and contour resistance matrix. Again, they are positive defined, but you see, they imaginary part, imaginary part. Next, Tirhov. I checked Tirhov. Now, tricky part. This is simple. I need voltages from the contour currents. I got currents, but I don't have voltages. In case you use contour current, this will help. It's much easier to solve equation, to solve this equation, to treat this equation, to get voltages. Spriegumne voltages, spriegumne konturstrālum. To get voltages from contour currents. Voltages by method of contour currents, voltages by method of contour currents, difference between nodal admittance and contour currents. Very nice, 16 digit. And now one tricky moment. Balance of power. When we need a power, here balance of power, power supplied by generator should be equal to the power dissipated by resistance. I hope I will have a time to take out this in detail, because question of AC power is a bit tricky. People make, even well-trained people do make mistake. At the first moment, I should write it. Power here, assume it to have imaginary part. The real physics is what there is an active part, heat or torque, mechanical, and part of energy. Capacitor charges, discharges, charges, discharges. It's a kind of back and forward wobbling energy. To reflect this imaginary part or reactive power for synchronous. Full power containing P plus imaginary reactive power can be defined as a complex value of voltage multiplied by conjugate value of current. What's the conjugation? If you have some x with point, its mirror will be a conjugation. So branch power is resistance of branch multiplied by branch current and multiplied by conjugation. For AMF, it's voltage multiplied by conjugation of. I hope I will be able to show it in detail. Why it's so. But here is a small, for the first, it's a very small piece of programming to check balance of power. It's a way to check your solution. Sometimes I saw quite tricky thing when network with inadequate number of nodes was solved, but you yield some result, and they appear right, but they were not right. and balance of power shows it, see? Nice zero. That means that solution is correct. What power supplied by generator is equal to power dissipated by green resistance and internal resistance of my coil. Balance of power correct. Okay, this was easy. It's an easy solution, but actually in real life most of solutions will be like this. The not easy part. Not easy part comes at the moment when you start to account magnetically coupled circuits, when you have mutual inductance. I have a set. This is self-inductance, 100 millihenry, and this one is a standard mutual inductance. You know what mutual inductance means? Huh? If you have two coils with common magnetic field or common flux, transformer on two coils and common magnetic circuit. So it's reflected as mutual inductance. Measured in Henry, actually under this it's a proportional factor. If you put 1 amp in the primary, what will be voltage at secondary? For 1 Henry, here, for example, this battery, 1/10, hundreds, thousands, and 10,000s of Henry. Fully, if I put all to 10, for example, not 0, 0, 0, 10, its inductance will be self, 1 Henry. Here I have mutual inductance of 1/10 of Henry. This means that if I put 1 amp at primary side, at the secondary side, what I will have? 1/10 of the volt. For calculus, mutual inductance appears as a mutual resistance. If, for example, I have branch 1 and branch 2, and they are coupled with mutual inductance. They are windings of transformer. I will have 1, 2 equal to Z2, 1 and equal to its mutual inductance. And this makes resistance matrix not diagonal, and that's why Jordan solution is needed. Where to point? Point. 1 second. I will find the place. nice without inductor. I will put it in place of capacitor. Disconnect. One microfarad, absolute units. Oops, something. It's manufactured in 1948.
Oh.
What a quality!
You are taking care of it.
Primary side, come here. Come here, come here, come here. Flows in, and then, and flows out. Yeah. And what will be on the secondary side? I need something to create a contour. I have second 600 ohms. Go here, and where the ground will be, I need ground. One problem with nodal technique, graph of the network should be it's okay, it's okay. Ground, 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 ground. Ground. Yeah, it's ground. Ground, 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 ground. Okay. It can solve network with SciLab. Network with SciLab can be solved. Connected and school. One moment. This is ground. Oh, blue line. 1 second. What is blue line? Now my network looks like this. 1 second. What is blue line? I have coil, resistance, resistor, ground, resistor, ground. be node number 3, and voltage and node number 3 we are observing at this moment. M, inductance. Oh, now my network looks like this. I have planned instead of capacitor, standard metal inductance with 100 millihenry capacitor. It has standard coupling of 100 millihenry. Parameters. 1 second, I'll just open yesterday example. Yesterday example, where are this one 600 ohms, it's easy, 45.9, this resistance is 45.9, this inductance 234.5 millihenry. This one at primary side 17 point, wait one moment, 82.77 millihenry, and small resistance is 17.5. Yeah. I will designate this as a branch 5. This will be branch 6. Yeah, really. In flows, that's mean what number 5 this way, number 6 outflows, and this small part will become one more contour C. Oh, here is my network. Wait one moment, where am I? To show it bigger. Here, now my network, I have instead of capacitor, I've put a transformer with non-neutral coupling. And what will I get? 1 second, we will solve it. I will save time. Here are M and N matrix from yesterday. Or maybe. Okay, I can left it. It's my yesterday solution. It's the same network, but I have added 2 columns for the 2 more branches. And here also this column and this column added to reflect what I have added. I can show one thing. I will temporarily disable these 2. See, I have a coupling between 3 and 5. Without these elements, what solution will produce? where are my voltage? Everything fine, but see, 0. And again, where are you? Where are my voltage? Nodal voltage. See, it is 0. 0 instead of 2 volts was there. See, 0. I have omitted a mutual coupling. Now I will put it back. This part, see, moment, actually this part, branches 5 and 6 are not connected to the primary side. Excluding effect of coupling, magnetic. And where we are, 2.74. You see it? 2.74. Again, in nodal voltage, 2.74. Scope. What are you showing us? What's on ball 1? 2.83. Scope thing with RMS of 2.8 and calculus show 2.74. Near. Near. We can live with this. We solved. What about current? Current in the last 4 milliamps. I don't know. Can I measure 4 milliamps? I can try. 1 second. Let's try to get. Oh, milliamperes AC. Let's see what we will get. Okay, RMS of this current is 4.14, if believe. Let's check. We need an absolute value of branch currents. What? Okay, absolute value for this current is 4.6 milliamps. By calculating, no, it's 15 volts, 4.3 milliamps. But we need to take into account internal resistance of net. 4.3 instead of 4.6. Near? Near. I think we can live with this. So, I think we solved an AC network. Yeah? Yeah. what's now? Attendance chart. 1 second. 1 second, I will get it. 1 second, everything solvable. Something. Oh no, it throws me. That's not what I need. Okay. It throws me to the main screen and I need this. We have 25th of September. 25th. This, we need this one. Please. 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 Yeah. I need first this. Tikko atrasti. Okay. One moment, we will see something. Fine, fine. You happy?
Yeah.
Yeah. You haven't registered for today.
Sorry?
Did not register for today?
No, I have no understanding.
Wait 1 moment, I will. 1 second, it will. Yes. Save. Welcome. See how easy so AC networks can be solved when you can copy from yourself.
Yeah.
I need to do one thing. I need to put this example on a learning system.
Thank you.
Welcome. When till I'm here, 1 moment, I will put it inside. Yeah. I will put this example to a learning system. And